7.1, the Pythagorean Theorem. There's actually some really interesting history that goes with this, but it sounds more boring when I explain it. I'm going to link some videos at the end if you'd like to hear about it. It involves Pythagoras and his dudes being way too serious about math. Now I know that you've used the Pythagorean Theorem this year, but we will do a little more technical work with it today, so stay tuned. The Pythagorean Theorem relates the lengths of the sides of a right triangle. It only works for right triangles, but we usually use a squared plus b squared equals c squared, remembering that the c is the important one. The c has to be the hypotenuse, because Pythagoras would have said the square of the length of the hypotenuse is equal to the sum of the squares of the lengths of the legs. The legs are the ones that are not the hypotenuse. Have you ever seen one of these things in like a science museum or something? It's supposed to demonstrate the Pythagorean theorem, but unless you understand what's going on, it probably doesn't make sense. Do you see those two squares at the bottom are filled with water? And both of those squares are supposed to be A units by A units, and the other one is B units by B units. And so the area of those two bottom purple squares would be A squared and B squared. And the Pythagorean theorem says that if you combine those two areas, it should equal the area of that top square, the c times c squared. So watch this. So we've got that a squared water, and it's trying to drain into the c squared. And now the b squared water also draining into that c squared. And we see that the a squared plus the b squared totally fills the c squared perfectly. This is actually how Pythagoras thought about this idea. He was talking about the area of the squares that fit on those two legs being equal to the area of the square that fits on the hypotenuse. Let's try an example. So if we go a squared plus b squared equals c squared, on this triangle, which one do I have to use for c? The one across from the right angle is the hypotenuse, so the c has to be x in this case. The 6 and the 4 are interchangeable. Since addition, the order doesn't matter. At the end, we take a square root to solve for x. Technically, algebraically, it would be plus or minus the square root, but since we're talking about the length of a side of a triangle, we'll just use the positive one. So I'm going to have you write your answers in 3 different ways. The first one is as a square root, so the length of that hypotenuse is the square root of 52. And if we typed in the square root of 52 on our calculator, it's not a whole number, but it comes out to about 7.21110. It's irrational, so you can just round to maybe 2 decimal places. Simplest radical form is what we need to talk about a little more in depth. I think you've done this in algebra before, but it deserves a review. Simplest radical form is when you write your answer like 2 times the square root of 5 or something. That's not the answer to this one. But what we're going to do is we're going to try to think of how we can break down the number 52 into basically something that has a perfect square root times something that doesn't. And there's a couple ways to do that. A lot of teachers will teach the factor tree method, where you try to find the prime factorization, is what they call it. So 52 is 2 times 13, or 2 squared times 13. Since we're interested in taking the square root of 52, we can think of that as taking the square root of 2 times 2 times 13. And it always turns out that if you can find a pair of numbers, 2 times 2 times 2 is 4, and I can do the square root of 4. But the square root of 13, we're kind of just stuck with that being irrational. And what is the square root of 4? 2. And what is the square root of 13? Nobody knows. It's some irrational number. So we just leave it as 2 times the square root of 13. That is simplest radical form. So the factor tree being one way, if you can get those down to all prime numbers and get the prime factorization, any pairs of numbers we'll be able to simplify outside of the radical. Here's another example. We've got a 16-foot ladder resting against the side of the house. Turns out you can't actually reach 16 feet up with a 16-foot ladder because you have to kind of position it away from the house. This ladder is positioned 4 feet away from the house. Let's see how high up the house it reaches. You can see that that's a right triangle, so we'll be able to use the Pythagorean theorem. Which one is the C? The hypotenuse, the longest one, the one that's across from the 90-degree angle. So 16 has to go in for our C. The other two are interchangeable. This time I'll square both of those numbers. This time I have to do just a couple more steps, like subtracting the 16 from both sides. Finally taking a square root. Again, we will just use the positive one since we're talking lengths of triangles. So the answer for the height of that ladder is the square root of 240, which is not all that helpful. So let's take a calculator, figure out the square root of 240 is 15.49. We call that our approximation. I suppose we should be labeling this as feet, huh? So it reaches about 15.5 feet up. Let's practice that simplest radical form again. So we're just going to think of some numbers that multiply to make 240, and it doesn't matter how you start this. I'm just thinking 24 times 10 seems kind of obvious. And you can split these down however. We'll always get the same thing for our final bottom numbers, our prime factorization. You'll know you're done when all of those numbers at the very bottom are prime. So we can say that 240 equals, what do we have? 2 times 2 times 2 times 2 times 3 times 5. And maybe you'd write that as 2 to the 4th times 3 times 5. And so when we think about taking the square root of 240, we think about taking the square root of these numbers. And anytime we can find pairs of numbers, that's happiness. We've got a pair of 2's. We've got a pair of 2's. And we're looking for pairs because we're talking about a square root, and pairs are squares. Anyway, so I would say that I've got that pair of 2's makes a 4. The other pair of 2's makes a 4. The 3 and the 5 are kind of just stuck inside, and 3 times 5 is 15. So I know that 15 will just kind of stay there. And then let's do all the square roots that we can. The square root of 4 is doable, 2. And the second one is 2. And like I said, the square root of 15 will just stay in there. So simplest radical form for the square root of 240 is 2 times 2, which is 4, times the square root of 15. And if you wanted to double check that, type 4 times the square root of 15 in your calculator. Should come out to about 15.49. This is the part of the video where you just sit back, relax, and try to enjoy this proof of the Pythagorean theorem. There's actually, I think, hundreds of proofs of the Pythagorean theorem. Yeah, I just looked it up. There's actually a book you could read for leisure that lists 367 proofs of the Pythagorean theorem. I'm just going to show you one. This is a pretty common one. And again, this is just for your enjoyment. This theorem requires that you're on board with me on a couple things. Would you agree that the area of this large square here should be equal to the area of the 4 triangles plus the square in the middle? I think everybody would agree with that. That's the premise that we start out with, that the area of the big one equals the 4 triangles plus the kind of tipped over square in the middle. The large square has dimensions of a plus b by a plus b, because it's a square. And so the area would be base times height, right? And all of those triangles are the same. They're all right triangles. They're a by b. So maybe I'll just pick out this one. Triangle area is 1/2 base times height. So So all 4 of those would have that same area. So for my 4 triangles, I'll just take 4 times the area of one of those, 1/2 base times height. And now we're going to switch to that blue square in the middle. It's a c by c squared, so if I take base times height for that buddy, it's going to be c times c. So far this doesn't look much like the Pythagorean theorem, but remember it's a proof, so that should be our final step, is saying that, oh, so then a squared plus b squared must equal c squared. So stick with me if you believe this so far, because smaller areas combine to make larger areas. Now you just have to stick with me on some algebra. Do you remember how to FOIL? A times A times B times A, B times B. So a times A is a squared. Our outside here, a times b, and our inside here, a times b, will give me 2 ab's. And then finally the last 2, b times b is b squared. 4 times 1/2 times a times b. We don't distribute because there's no plus sign. So I can just do 4 times 1/2. Half of 4 is 2 times a times b. And then over here we had c times c. We'll call that c squared. This is starting to have some Pythagorean theorem look to it. I did notice that I have some matching things on both sides, so I'd be allowed to subtract 2ab from both sides if I wanted to, leaving me on this side with a squared plus b squared, and on this side leaving me with c squared. And so if you believed all those other steps, then you have to believe that a squared plus b squared has to equal c squared. And remember that a, b, and c stood for the lengths on that right triangle. So that's kind of fun, just some math enjoyment for you today. If you watch my history videos at the end, you'll know that Pythagoras didn't believe in things that weren't whole numbers. So Pythagorean triples are numbers that work in a squared plus b squared equals c squared that are whole numbers. So here are his favorites. A 3, 4, 5 triangle. 3 squared plus 4 squared does equal 5 squared. And then any scale factor of that same triangle would also work. So all of these sets of 3 would be considered Pythagorean triples because they work in the a squared plus b squared equals c squared formula. We can form a nice right triangle out of any of these whole numbers. And so if I asked you, are 10, 11, and 15 a Pythagorean triple? Well, first of all, they are whole numbers, so they're candidates. What we'd have to check is, does 10 squared plus 11 squared equal 15 squared? Not quite. So 10, 11, and 15 would not make a right triangle, and therefore they are not considered a Pythagorean triple. If you're interested in some of that history of Pythagoras and his theorem, these are probably my favorite videos that I found so far. Highly recommend.